Well, it's my pleasure. I sent a message to Sarah and asked her if she'd speak. We had met probably 12 or more years ago. They were working on some technology. I had some interest. We got close and didn't quite get there yet, but sounds like that's where they are now. Sarah is the CEO and co-founder of Skuld, a company that's focused on advanced manufacturing and materials. And Sarah is an inventor of a new process, and it's a new advanced or a new additive manufacturing evaporative casting. So many of you probably are not going to know what lost foam casting is. Hopefully Sarah's going to delve into that a bit. But she's merged that with 3D printing, which is really interesting, because how do you create a shape? The old way with lost foam is you had an aluminum tool and you injected foam and had to cure it, and it was a process in itself just to get the foams. Sarah's got a degree, quite a few degrees, in metallurgical engineering, material science from Ohio State. She's got an MBA from Carnegie, and she's finishing her PhD at WPI. I didn't even know that until I saw it on your bio, and that's where I got my PhD, is WPI. So, without further ado.
All right, hopefully you can hear me.
You should sing something.
For this YouTube later. So, thanks everyone for attending. Hopefully you'll find this of interest. I'm actually talking about a bit broader than just our technology. Kind of wanted to start and give you some background just about additive and casting in general, because there are a lot of options there, and didn't want this just to be, you know, a marketing spiel. I'm happy to give that some other time if you want that, but I'm talking more broadly about these topics. So, as he said, my background's in metallurgical engineering. My dad's a ceramics engineer. He taught at Hockin College for years, so I grew up always around that materials field. And, you know, a lot of people don't necessarily know that, but the eras of time historically have been named after the types of materials that were most prevalent. Everything from Stone Age, Iron Age, and then more recently, talk about the steel and silicon age. There are a lot of casting processes. So a lot of people just think, oh, that's just casting. This is one method of things being classified, and these are like the conventional casting processes. They tend to group them by the type of mold, type of patterns. Some of these things you might notice, I don't know if there's a laser pointer here, but some of these are not things that make castings, right? So people don't typically talk about the steel mill processes as making castings, right? You're doing casting, but you're making bars or I-beams or, you know, ingots or whatever it is. But all of these things start out as castings. And there's also a lot of additive processes. So a lot of times people talk about additive manufacturing or 3D printing, and I don't think they necessarily have respect for the number of processes that are under that banner. AM Power, which is a market research company out of Germany, they have these very nice infographics, and actually if you see them at a trade show, they'll have these posters that have all of the brands that are under each type of process. So according to them, there's 10 ceramic processes, and you might notice this gray one here, that's sand. So they're talking about sand printing in that case. So that will come up later. They say there's 16 polymer processes and all kinds of different means. And then they count over 20 metal processes. And they kind of give up and they just say miscellaneous, and they just kind of group a whole bunch of extra things that they didn't feel like, you know, dividing out separately. So some of it, so they didn't used to include cold spray, but I guess they thought cold spray got big enough that it got its own part of the pie chart. But some of the other things that aren't listed is electrochemical additive. I used to work at Fibersonic, which we focus on ultrasonic additive, which is a sheet lamination process. And then there's all kinds of other things that aren't listed. And there's new things being created all the time if you go to industry trade shows like I do. And one of the things that's not listed on here is casting. So when they define additive in metal, they're talking about metal as the feedstock, not that you're making metal. But from my perspective, that is misguided, I guess I will say. Because like I said the other day, most people don't care about the feedstock, or really, they don't necessarily even care about the process. They care about the part they want. And they care about that it meets their requirements, not necessarily how it got there. And actually, most people don't even care if it was machined or additive at all. They just, they want that thing, whatever that is. But currently the industry, they group things by raw material and a lot of times by these AM families. So at least in my perspective, the metal chart should be bigger and include the casting options. There's at least 6 or 7 of these, depending on how you count, maybe more. But I'm going to talk about them here a little bit more depth before I get into like what we do at Skuld. But we create sand. There's a variety of things for investment casting, for tooling, etc. And so how many out of these options there are really depends on how you count options. So several years ago, someone trying to organize this, and they said rapid investment casting, and they had all sorts of different processes and manufacturers on here and ways that you could do this. And of course, this is over 20 years ago, so there's far more options if this was updated now. I actually had updated it with things that we do at our company here. We do AMEC, which is based on 3D printing polymer, but we also will machine foam, so that is also a rapid way of getting castings. But I'm not going to talk about that too much today. So why would you want to use AM instead of these direct metal options? I know a few, months ago you had someone, I think from Bello come talk, because I saw that on the website. So they're already doing powder bed fusion, 3D printing, so there's a number of reasons that people are really starting to look at AM for casting, especially. This is very much driven by the military and the government. So one of the problems, direct metal additive costs a lot. It can easily cost more than 10 times more than your traditional casting. So if normal steel casting might be $2 a pound, let's say, you're probably minimum starting at $20 a pound, and it could be $1,000 a pound for a lot of these things. So that's one problem. Some applications it doesn't matter because it's low volume, it's very specialized, it has some other savings. There's reasons that people will pay those things, but also it can be an issue because there's only certain industries that are going to be willing to pay $1,000 a pound for a steel part. Maybe defense, maybe medical, maybe aerospace, certain applications, nuclear, certain applications, but you're not going to build an entire tractor out of 3D printed metal parts because nobody's going to pay that. Another issue is that they're rate limited. So your typical additive equipment is putting down things on the order of pounds per day. And I'm used to dealing with tons per hour. So that is an issue for scaling. You can of course scale by buying many multi-million-dollar machines, but at some point that's also an issue, and that's contributing to the cost issue. There's also an issue with what they call qualification. Basically, at some level, people don't really trust these materials because you're essentially blowing up metal powder and welding it back together. So the number of tests and things that you have to do is enormous. So it can take months or years, and millions of dollars to qualify a given alloy. When I worked at Fabrasonic, it was going to be like basically $2 million of materials testing to qualify our process in just 6061 aluminum. So one alloy. And that's repeated for like every process and every material combination of millions of dollars. And I recently learned, because I thought that once you got the material qualified that you were done, and I was told, no, every time you make a batch of parts, you probably have to do another $3,000 in tensile testing to qualify that batch. And it's just like shocking amount of testing. And part of this comes down to the fact that a lot of times they're inspecting inequality in these processes. So they're using CT scanning to verify there's no defects. They're using the tensile bars to make sure nothing changed. But I've also been in a lot of technical talks where if you calculated the -3 sigma, right, the normal distribution, this is where your material properties, yeah, I know I was talking to somebody earlier who had SPC background, right? You know, that you think 95% of the data is going to be within ±3 sigma. Well, when that -3 sigma is below 0, you have a problem. And that is one of the dirty secrets of direct metal additive, and a lot of times that is what is happening in the data. And that's why they're inspecting inequality. So, I will get off that rant for a little bit. But I'm going to talk about additive and casting. So, there's a number of ways that this is done. So, probably one of the most common ways this is actually done is by printing tooling itself. It's not to directly go to the casting or the mold or the pattern, it's to print the tooling. All those other additive processes I showed you, they could be used for printing tooling in theory. Most of the time people are using desktop FDM printers for that because they're cheap, they're readily available. You can join them to get, join multiple prints together if you're trying to make something large. Relatively inexpensive if you're doing it that way. Although bigger parts, sometimes you're going to have to, people will print on other materials, and sometimes you have to have a tool that's metal. So the main reason people will be doing this is that large metal material for tooling, particularly ingots, size, very thick, these things are exponentially increasing in cost as you go bigger, and they have really long lead time. Like if you didn't plan for your die for Toyota like 2 years ago, and now you suddenly need a different one or it's defective or whatever, like you might have a 18 to 36 month lead time to get that new metal ingot for that mold. So that is a lot of the issues where people are wanting to print tooling. But a lot of times people are still seeing that it's beneficial just to machine things. Printing tooling has a lot of higher cost. Sometimes especially if you're using polymer instead of metal, it's going to have shorter life a lot of times. And then what we've seen in lost foam, because the American Foundry Society has paid for a lot of research in these alternate materials for making the foam blowing tooling. Typically these things all still need machining. So that's part of like why you're not really necessarily beneficial doing that versus a piece of aluminum plate. Because if you're still going to have to program the CNC machine, you're not saving that much having printed material in the first place. And then the other issue, especially when they tested ceramic and polymer tools, is you can make foam that way, but the thermal conductivity is so much less that you end up taking something that might be a 2 or 3 minute cycle time, and now it's a half an hour cycle time. So that's not very good for productivity. So typically, people are wanting aluminum molds for, at least for making foam. There are some companies that are focused on making tooling specifically for the casting industry. I've highlighted 2 of them here. Mantle has an interesting technology. I don't exactly know what they call their technology, but they essentially put down this paste material, and then they machine it back, and then that's how they get the tool. And then Titan Robotics, they have a giant polymer 3D printer. It's also hybrid, so it's designed to account for the fact that you might need tighter tolerances and have to get the tooling required tolerances. So to move on from tooling, talk about additive and die casting. I'd say this is the area that has, I guess, the least options besides just making the tooling. They will use various methods as well to make inserts. And that can particularly be helpful if you're trying to deal with something that has wear surfaces, and maybe there's just one little area that's getting messed up. So they might just use an insert and replace part of the tool in a certain spot. It's also sometimes possible to iterate faster if you're using the added versions. But big cons in that typically die casting is going to require metal tool still typically, possibly for permanent mold you might be able to have aluminum or copper depending on what you're trying to cast. But typically these are steel and they're typically relatively big, so now you're going to go back to this original problem of these printed metal parts are very expensive. So people are not typically printing the whole tool, although sometimes they are doing this for conformal cooling benefits, just because of the cost. There is one company that markets themselves that I am aware of, that specifically markets themselves to the die casting alternative, which is Foundry Lab. So they have a very interesting system in here that is essentially what I consider a kind of emerging category, which is a micro foundry. So this whole thing is a foundry. It makes your mold, it melts the metal, pours the metal. So it is very interesting in that it's an all-in-one system. They market it as a substitute for die casting, but as a metallurgical engineer, again, if your mold's not metal and it's ceramic binder jet mold, that you're not going to get the same representative properties as if you had used a metal mold. But people are using that for prototyping. Oh, yeah.
Every time you come up with a con, it seems like it's a fatal flaw.
I don't necessarily think that. I mean, people use these, so I mean, they're drawbacks.
Higher costs?
I mean, there are reasons people use these, so it's not like they don't use them at all, right? There are pros and cons to everything. Would I choose to use this if the metallurgy properties were super critical? No. If it was close enough or it was less critical application, and if I'm doing this for a prototype, maybe it's adequate. Or maybe you prototype it that way and you test it and it works, and then you can just keep making it this way. Is it die casting? No. The other interesting thing about this is that they are melting with microwaves, which I think is an interesting approach. Most foundries will melt with, gas, resistance heating, induction. I'm not aware of too many other approaches using microwave to melt the metal. The other thing that's a drawback, I think this one's probably more severe, is the fact they only have 6 alloys. So there's thousands of metals out there. So that's probably more limiting, because I guess it's maybe great as long as you can live with the alloys that they have set up in their process. Green sand and resin bonded sand. So these are probably the most common casting methods. If you don't know what green sand is, it's basically sand, clay, and water mixed together. It's called that because I guess historically green meant wet. Like green wood means it's not dried out, so green sand is that it's got moisture in it. This technology's been around for over 3,000 years, so lots of things are are quite old technologies, but then still useful today. But they are using additive in that process as well. So green sands typically got about plus or minus 3% tolerances, which means in a lot of applications it's going to need machining, sometimes substantial machining. And because of the fact that you're just packing together wet sand kind of bonded with clay, it is a little bit more limited in the geometries that you can achieve. Resin bonded sand, I think that was invented in like maybe the 40s or 50s. It's basically adding glue to the sand resin to make it stick together. It can have a lot more complicated geometries. It can also have larger parts, but often it's getting very significant machining. If you've ever been in a no-bake foundry, you will know what I'm talking about when I say it's more polluting, because when you pour those molds, that resin is getting burned during the casting process. So green sand, they will use it for, they will use printed tools. They will also sometimes print cores. So it'll be like the green sand mold, but the core itself will be 3D printed with resin. That's probably the most common way. As far as I know, there is no system that exists that 3D prints green sand. It might be interesting for somebody to study that at some point, but there's concrete printers and things like that, so there's no reason I think it couldn't be done, but I'm not aware of it. So there's a lot of benefits for this for tooling. It's particularly good for small runs, prototypes, things like that. Again, they will use prints for certain key areas where there's wear items, just like in die casting. And the con is you're not going to have these tools last the same way you would like a piece of machined aluminum, like on a Giza or something like that. The other thing is, in general, if you're just printing the tool, you're not getting the new design capabilities typically. Resin bonded sand, on the other hand, they will sometimes 3D print tooling, but more frequently they're using a process called binder jetting, where they basically will put down a layer of sand, and they have a process where they make little glue droplets that build up the structure. This is being used primarily for printing cores. Sometimes they will print the whole mold, but it takes a lot longer and costs more than if you actually did the rest of the mold in the conventional way. Some of the big benefits for this is you can have more complicated geometries with these printed cores that you would be difficult to mold. It can also consolidate what might otherwise have been lots of cores that had to be like manually assembled, and they can just 3D print what becomes one core. When you consolidate cores, you eliminate this kind of stack up error by trying to assemble these. So that's the main reason I see that they're being used. Also for very short runs or sometimes legacy replacement parts, prototypes, things like that. It's being used fairly regularly. The biggest drawback I see here is actually that I think it's reflective of the market. Almost all of the sand printers are owned by the pattern shops, which basically shows that it's not necessarily enough of a business case for most foundries who do sand casting to buy them themselves. So they rely on the pattern shops to be the places that they buy these cores or molds from. So that kind of goes to the expensive nature, the equipment's expensive. There's a number of issues as well, like with print heads clog frequently and things like that. So, lost wax investment casting. So, who here is familiar with lost wax? All right, you have a couple of hands. All right, I bet most of you may be wearing a lost wax casting on your hand. If you're wearing a wedding ring, good chance that's how it was made. Lost wax is used in everything from jewelry to turbine blades, but it's actually the most oldest foundry technology, going back nearly 6,000 years. I guess around the time humans invented pottery, they invented the ability to cast in ceramics. But high level how lost wax works is you make the shape you want in wax, you put a very thick ceramic coating on it, you let that dry, maybe there's a whole iterative process of this, but ultimately you melt off the wax and remove it, and then you have a hollow space that you can pour into this ceramic shape to get the part you want. So limitations of lost wax, you can't I've never seen it make really large parts. Typically, they're making about 120, 150 maybe pounds or less. It's very good for very small things like jewelry. There are some challenges with internal passages. You can make internal passages, but what happens is that ceramic is inside the passage, and then they have to dissolve it with sodium hydroxide. So that's kind of a nasty process. It's possible, but people try to avoid it. And the biggest drawback is that it's a slow process, especially for bigger parts. You're talking process time 2 to 4 weeks of process time, not queue, not lead time, just like the steps of how long all these steps take. So if you're using 3D printing, you're typically having very similar process time. You make it a little bit faster, but typically that is an issue. But at this point in time, additive investment casting is pretty much always what is used for prototypes. I've been told that like nobody is making tooling anymore in investment casting until the design is locked down. But if it's a prototype, it's going to be done additively. It's also a very good process for very small things. Actually, if people come to us with inquiries, if they're very tiny parts, we will just direct them to one of the other additive investment casting people. They also have issues when they do print like this with ash getting caught inside of the mold, which causes metal defects. They have problems with the molds cracking due to the thermal expansion of the print when they try to burn it out. There's all kinds of challenges in these areas, even when they are being used. But due to the cost, that tends to be a recurring theme. And typically, if it's not a custom low volume thing, at some point they will switch to tooled standard lost wax. There's also additive for directly printing the ceramic shells. I actually had a tour very recently at a company called Aristocast, which is up in north of Detroit. There are other places that are using this, but basically they use resin printers that are full of ceramic in that resin, and then they can print very highly intricate ceramic shells. Aristocast told me that they actually had developed a process to be able to make the famous GE fuel nozzle, which is a big additive thing that was developed with hybrid fusion. They demonstrated that you could make it this way as well. They had things where they were making suppressors, like some pictures here off their website, very complicated shapes can be made this way. Drawbacks, you still have to divide and basically get rid of that polymer part of the resin, and then you have to center the shell. They often will still assemble this on a wax tree, so it's still going through this very long process, which is why these still tend to take several weeks of process time. These printers, I'm not aware of any that is more than about 8-inch cube. I think is typically the size that I've seen on these. There might be a few slightly bigger than that, but they're not making anything gigantic this way that I'm aware All right, so now I want to talk about what we do. I'm giving you all this background on other ways that you could use additive. So I'm going to take a little detour into lost foam, which is the parent process of our additive process. The loss. So who here is familiar with lost foam? I know one person. Okay, handful. All right, great. I will give a brief overview for everybody else. So, lost foam is a variation on investment casting. Instead of wax, you make foam, and we will still assemble it in a cluster or tree kind of situation, similar to lost wax. But one of the key steps that's different is that our ceramic coating is about 1/100th as thick as traditional investment casting. So whereas traditional investment casting, the shell might be 3/8 of an inch thick, let's say. In lost foam, it's about 3/1000 thick. That shell is not, we don't even call it a shell, we just call it a coating. It's not structural. So what actually holds everything together is the fact that after the coating dries, we vibrate sand or ceramic beads around that coated foam. And people always are like, oh, so you're printing the mold. And I'm kind of like, it's not exactly a mold. It's a little ambiguous because typically a mold means a hollow space. But there's actually no hollow space. It's sometimes called full mold because of this. So what happens is you pour the molten metal on the foam, and the foam vaporizes, and simultaneously it fills in where the foam had been. So this is how this process works. This kind of shows a little bit of the diagram of the physics of what's happening. So molten metal, heat front, melts and then vaporizes the foam, and then that gas is shoved out the coating wall and out through the ceramic beads. And so that enables the metal to keep flowing forward, and that's how you get your metal part. So I kind of went through what these differences are between lost wax and lost foam. There are benefits to both processes depending on what you're trying to achieve. Lost wax does have better tolerances, it does have better surface finish. I would prefer that process if I was making very fine, intricate, detailed things. Lost foam, on the other hand, can make bigger parts. It's better at interior channels because it doesn't have that thick ceramic there. And where it really is better is on process time. So several weeks versus, in some cases, as little as 3 hours. I'd say a day or two is more typical. I mean, that's like we are super trying to expedite things. Now there are other additive methods with lost foam. You could print tools. You could also do what's called there's some people who have a process called LOM. It's basically they machine foam in thin strips and then glue it together. I'm not actually aware of that being commercially used, but it's been in the research papers. There's also people trying to directly print foam itself. I think that's still in the research state as well. And then there's what we do, which is we 3D print a polymer to use instead of foam. So I kind of talked about this already, about like how most of these things don't, for the object manufacturing and printed foam, don't seem to really be used. So kind of the reason I went over how lost foam works itself is that our process we call AMEC, additive manufacturing evaporative casting, is a very similar process. Basically, we make a 3D print instead of the foam, but the rest of the process is the same. I did bring, I need to remember to hand these out because otherwise I totally forgot. I did bring an example here of a print, a part that's been gated together. It's not coated yet. And then the final casting for metal gear that we made. But the process is very similar. Ceramic coating, let that dry, compacted ceramic beads, pour metal on top of polymer, vaporize it. Yes. One thing you will notice looking at the resulting metal, it's very much what you see is what you get. So you do tend to see the print lines or print defects, as the case may be.
How do you get rid of the permeable? Is it the mold sand pretty permeable? What are you using as a media around it?
Yeah, we use ceramic beads, but that's what we use in regular gloss foam as well. The main reason we use beads is actually more for silicosis risk. So silica dust, or silica sand turns into silica dust, which causes lung problems. So the beads cost more up front, but then they don't have that problem because they don't wear away. So it's kind of like a much higher one-time investment.
But do you have better permeability with the beads?
I think it's not significant. I mean, I think it's just, if you buy the right sand, I think it's the same. Because there's definitely like places that use sand for lost foam, and
Oh, I know that, but I'm just thinking your polymer.
There are people who we've used sand before. I mean, and so have Indy used sand. We did a lot of the initial work at their facility. And I know that, I don't actually know what Mercury Marine uses for their mold media, but I know they're doing work development in this kind of process.
They have a blend. It's a blend of sand and beads. So
Interesting.
I've been there.
I did not know that.
But predominantly it was for permeability, to get rid of the resin, the gases from the evaporation of the media.
Interesting.
Yeah.
Okay. It's not shown here because in this case we weren't using it, but sometimes we do apply a vacuum. That also helps pull the gas off, the vaporized gas. Because otherwise what happens is it just kind of percolates to the top and starts burning right where you're pouring. A little bit of history of why we started. So my background was in casting and lost foam, and American Makes, and the Youngstown Business Incubator had a pitch competition, and so we wanted to solve what was our own problem, which was the tooling cost in lost foam historically costs 6 to 7 figures per part number, and so what we were trying to do is, well, what if we don't need tooling? What if we can 3D print it instead? So first trial did not go well. It's all the explosions. We did this trial at the Coronado Steel up in Youngstown. None of the print came out. We just got some of the gating system. Eventually we got to kind of like parts, kind of looking like parts. This was a skull. It's kind of cool looking, but not what the print looked like. This was a Squirtle. If you're familiar with Pokemon. This was just some kind of base. So it's kind of like getting closer. Eventually we did get a part to come out that looked right. So the first successful AMEC part was this Pac-Man Ghost. At the time, we did not know why this part worked. But we knew that at least the process was feasible to make parts. Over time, we've developed the technology a lot more. We're starting to build computational models now that we're getting a much better understanding of what's going on. We're also developing all kinds of other alloys and capabilities, thin walls, ability to do threads. This part here was an Inconel die. So yes.
trying to make sense of all this.
Okay,
I assume this was 3D printed,
yes,
that you then take ceramic beads and put them around this thing. You then pour metal in and get that.
correct.
Well, you missed a
You
step.
missed the coating step because I didn't bring a coated part of it.
You have to take that piece and then coat it with a ceramic, and then you invest it into the.
Yeah, so see how that one's different looking than this picture here with the, where it says coated assembly? That has, I probably should have brought one of these, but I didn't have one available. But the ceramic coating basically looks like a paint. And it's very thin, but that's the stuff that's kind of, so you assemble what you have in your hand, you put the ceramic paint on it, let that dry, and then you vibrate ceramic beads, and then pour metal on it, and then, yeah.
So it's, the coating becomes the mold for this?
So, if we go back to this, what happens is like, in lost foam and AMEC is that, right, so that actually does have some hollow space, but essentially I guess you could consider all of it together becomes the mold. It's just that it's filling in.
I'm familiar with the green sand method, which you take that, you force it into sand, the sand keeps the shape, you take that out and you pour metal in.
This stays in.
Yeah.
That what you
So
have in your
I think
hand,
the difference-
it's coated, it stays in there, you pour metal directly into that, and that goes away, and as it goes away, your metal.
Oh,
ends
so the
up-
metal's on the inside of this?
The metal, that goes away completely, and the metal replaces it.
Yeah. So it's like
Oh.
filling in and vaporizing
okay.
at the same time.
So you don't need the,
You don't have to.
The green
jolt-
sand
The
on
jolt
the
squeeze.
outside.
Yeah. So what we call it the sand. And it could be sand or it could be ceramic beads. Like the key difference is that it's not bonded, it's just loose, so it vibrates together, and so it's just like packed together while you do this pouring
the
process.
mold stays in there. It's plastic and it's 3D printed.
No, it gets vaporized, so that's like, it's kind of a different way of thinking about it. So I guess if we wanted to say where's the mold's this, it's this gap, all right? So you have metal, foam, and then it's filling in, and it's making a tiny channel as it fills in and gets rid of the foam. Does that kind of make sense?
Entertain another question. I expected to see that form of the solid. You printed the shell. Is that what you molded?
Yeah, typically with the additive version, so if it's the foam version, it's solid foam, it's just very low density. When we do the additive version, we try to print as little as possible. So it could be entirely hollow, it might have some infill. It depends on what we're doing.
So what's the size of the ceramic beads?
Oh, I don't know that.
They're real tiny, right?
Small, yeah.
Right.
Bigger than metal powder, but smaller than, I don't know what size that is.
Your bowls have to be supported. You're pouring in fairly heavy metal. And you think that shell that
So,
retains them is fairly fragile.
It is supported by the sand and the beads.
Well, you had a vessel there,
yeah.
the cylinder.
Try to find a picture.
So that backs up.
Basically, it's a flask, it's
Yeah, it's
almost
basically a metal box.
a metal box or cylinder, and all that process is inside that cylinder.
Yeah.
And when you go and you can rotate that and dump it out, and then just take the parts out.
Yeah, let me see if I can find a better.
Sorry, Ned.
Oh, no, that's okay. Let me see if I can find a better.
Unfortunately, I'm no more. I played around with a bunch with you guys, so.
Find a better picture. So, this kind of shows the flask. And then, this shows a demo we did, I don't have this. So we did a demo last year at a military conference called Jay Dammit, where we basically took over the street of Harrisburg, Pennsylvania, and we're doing demos. So in this case, the flask was just a 20-gallon steel drum, right? So that's what's holding these vibrating ceramic beads with the print and the foam gating system in there.
So one of the advantages to your company is the ceramic coating. It keeps the detail and it keeps that thinness of the shell down. That's what I'm seeing, right? That's one of the things that sets you apart from some of the other processes?
I would say the main difference is a couple of things. One is, which is probably going to segue back to this. You know, for us, we also do lost foam. So we tend to use this process as a prototyping method. So it's not quite as accurate as regular lost foam, but still far more accurate than sand printing. We think it's about plus or minus 0.5%, whereas sand printing is more like plus or minus 3.5%. But the other way that it's better is it's much faster. So instead of taking weeks like in traditional investment casting or additive investment casting, or like when you're powder bed, not powder bed printing, binder jet printing, it still takes a long time to build up that big structure, right? We are only having to print the surface for the most part, so it's a much faster printing process. And so we've actually made AMEC parts in 11 hours, like that's the fastest we've done, and then in regular lost foam we made parts in about 3 hours. Like that's where we're like, kind of.
And what's the longest process within that? Let's say the 11 hours.
Well, okay, so for lost foam, the longest step is drying.
Yes.
And then in AMEC, it's kind of a tie between the printing process itself and drying. Yeah.
And that's the problem with investment casting too, is you're putting multiple layers on,
Yes.
right? You may dip 15 times. And each one of those you have to dry, and that shell has to be dried before you can pour metal into it, because you're gonna have to preheat it. If it's wet, you're gonna have steam and all kinds of explosions.
Yeah. I guess the other benefit I would say is cost. So while there's a certain amount of cost on the first piece, right, this non-recurring engineering, you got to do that on anytime you do something the first time. Once we know how to make something, the costs come down dramatically. We're using low-cost desktop printers. We're using PLA. We're just printing the surface. There's like all of these reasons that the cost is substantially less. Now there are limitations in our process as well. NRE, as I mentioned, there is no computational model for lost foam that works, let alone for the AMEC process. We're working on developing that, but it's somewhat limited by the printer accuracy. Limitations on what we can do. Yes?
You still have to machine the final piece.
That depends, right? So that's very much a question of what's the required tolerance.
That'd be a major labor cost savings.
Right, so it depends on what's the requirement. So usually our goal in lost foam or AMEC is net shape. Sometimes it does need machine stock because somebody wants a really high tolerance. Typically sealing surfaces, the surface roughness is not enough. It really depends on the design requirements. And another thing, we are still, this should be LB and not DL, but we are not able to make as big of parts yet in AMEC as we can in regular lost foam. So regular lost foam has made several ton parts. We've made up to about 900-pound parts. The limitation so far has been a 150-pound part. We've been trying to make this 250-pound veggie boat, and it keeps delaminating, so we're still working on that. Trying to figure out ways to make sure that as you go bigger, that the print itself doesn't crack.
Do you support the inside of that polymer?
Sometimes, yeah. Well, sometimes it needs it because of the sand, but sometimes it needs it because of, so it's very hard to print flat, blocky, chunky castings, which is how most castings are designed, right? So a lot of those geometries don't lend themselves to polymer printing because they are just like in this big flat space. So that actually leads us to another thing we sometimes do, which is we actually will merge these processes together. It's not just all or nothing. So, okay, this has a lot of covered the animations. So sometimes we will merge them. So this is a case study we actually talked about at the AMEC conference this year. In this case, we were working with heat treat baskets, and the customer wanted threads, and being able to vary where the threaded post could go. So we actually developed a way of prototyping it where we would machine the foam, and then instead of, it's very difficult to machine threads when you only have a 3-axis mill for machining foam. So we actually made the threads by 3D printing a little insert piece that we just glued in there, and then that was able to make the threads. So this is showing kind of coating and drying, and then the cast version of it. So, like I said, we mainly use this process for our own prototyping, with the goal of actually getting people to use lost foam. We are also doing a lot of work with other, particularly the military, on equipment for them to be able to use the process themselves. So I guess I'll end with one thought, and just if anybody has other questions. But I think somebody asked, like, is it all cons? And I think, everybody's saying, right, but if you only have a hammer, everything's a nail. Well, I think it's important to be aware of all these processes and the options and where they're good and where they're bad, because there isn't just one process, and like we don't even just use one process, right? We have CNC machining, we do lost foam, we have machined foam, we do additive version, we'll mix them all together. It really depends what we're trying to do. So with that, if anyone has other questions, yes?
I had a question about, is there any patents associated with the process of licensing? Or?
Yeah, so we have a patent pending on the AMEC process. It's been approved in Europe because they're apparently a little bit faster than the US patent office. And then we have a couple patents on equipment, and then certain materials that we're doing. One of the innovations we've been working on in lost foam and in AMEC is the ability to be able to cast rock grades of aluminum. So we've been able to do 60, 61, 70, 75, and other grades that are typically not cast. So we have patents on that, depending on that too. Yes?
You mentioned a couple metals that just don't work well in additive manufacturing. Do you think there's going to be a change in that?
So that.
Tungsten, I forget what metals were, but.
Oh, yeah. Well, that was unique to our process. So, yeah, so lost foam. So titanium needs to be kept in is very reactive, and it needs to be kept in a vacuum. So while we've never tried it, our expectations are that it would probably explode because we're creating a polymer gas that degrades into water. We don't think that it would play nice with titanium. Now magnesium, I have seen papers out of Oak Ridge that claim it can be done, but I don't know anyone doing this commercially. We've never tried it. I'm not exactly sure what sort of magic pixie dust is needed to make it work. but, because magnesium is also very reactive when molten, so that's kind of clear to me how they got that to work. And the other thing people sometimes ask me for that I'm like, okay, that's not gonna work, is like your refractory metals, right? Like those metals melt at higher than the ceramic temperature would melt at, so like that would probably, like tungsten probably would not work without some major re-engineering of the whole ceramic system.
So what are the alloys that you can do today?
Yeah, so mainly we can do pretty much anything that can be air melted as long as it's hot enough. So aluminum and above, aluminum, steel, iron, copper alloys, nickel alloys. We've never tried tin, but I don't think tin's hot enough. I don't think it would like vaporize.
Ductile iron?
Yeah, we do ductile iron, like any of the cast iron grades. And we have sometimes done grades that are typically vacuum melted, like Inconels, but they get contaminated with oxides, so there's kind of a property hit when you air melt those. It's not due to the casting process. The same thing would happen if you poured them in the sand mold.
Any innovation on surface finish improvement?
We've done some work there. We can make it somewhat smoother, but it's still not going to be investment casting. But there are methods to make it a little bit smoother.
I have about 3 questions. Right around here in your presentation, you mentioned HU and HK as alloys. What were those?
Oh, those are, they're called stainless grades, but they're like 40% nickel and 10% chrome or something like that. They're like super high nickel, chromium, high temperature alloys. These particular alloys are used for like in the heat treat industry because they're going up and down and like heat treat furnaces.
All right. In the still talking about alloys, one of your first remarks was that we're developing alloys. My guess is by that you may have meant we're not inventing new alloys. We're finding alloys and exploring their compatibility with this. Is that correct, or no? You're trying to come up with new alloys to address issues here. What did you mean by that?
So sometimes we do make what I would consider no-grade alloys that aren't. That's some of the research we're doing with DARPA is to make things that are not conventional alloys. But yeah, generally we're using new alloys in the process.
And then my final question was, you mentioned with investment casting, after you've melted out the wax and burned it to get rid of the residuum, you still may end up with ash. Here, you still have the possibility of some remnant of the polymer left in there. Is it less an issue because you have so much less of it, or choice of materials, or process parameters? Or is ash still something of an issue?
So what we think is happening is the reason we don't see an issue with ash is that ash is a remnant of burning, and the burning doesn't happen in the mold, it happens outside. So there's not enough oxygen and then that polymer gas gets pushed out.
Okay.
What we do see is about 0.01% carbon absorption in the metal.
If it can, and
Yeah.
it can.
Yeah, so like people ask us for like 316L, that typically is very difficult to get because like you can exceed that.
Iron content.
Thank you.
Is that it?
I had a question. You talked about green, we were talking about green sand and the resin that they use. What is the actual thing? What causes the pollution out of the resin?
I mean, I'm not a chemical engineer, but I mean, it's just that you're basically, burning.
The resins are typically
petrochemical-
urethanes. They're
Yeah.
urethane. They're a urethane
Yeah.
resin.
Okay,
So
Yes.
thank you.
I used to do that for a living or so. Urethanes.
Yeah.
Polymers.
Yeah, and I guess kind of related to that, so we actually aren't legally allowed to do those kinds of castings because lost foam is considered de minimis for air pollution below about 10,000 tons a year. And so we worked with the EPA to, get them to agree to that. But if we were to cast green or resin bonded sand, we would exceed the air emissions at about 1 ton per year. So it's like drastically different. All right, thank you.
Pleasure.